Welcome to The Explainer. Today, we're going to crack the code on a concept that's pretty fundamental to our entire digital world: hashing. It's really the secret sauce that makes finding information so incredibly fast, and we're going to break it all down right here.
All right, so let's just dive right in with a question that seems, well, kind of impossible, but it's something you deal with every single day without even thinking about it. When you search for a contact on your phone or look something up online, how in the world does it happen in the blink of an eye?
I mean, think about it. If your computer had to check every single piece of data one by one, the internet would just grind to a halt. Searching for a single email in your inbox? Forget about it. It could take hours. We need a system that doesn't just look for things, but somehow knows exactly where to look.
And that's where this brilliant shortcut comes in, a kind of magic filing cabinet for data. This is what hashing is all about: creating a super efficient, super clever index to find things without having to do a long, boring search. At the very heart of this system is something called a hash function. Now, the best way to think about it is like a super efficient receptionist for your data. You can give it any piece of information, your name, a phone number, a huge file, whatever, and it instantly gives you back a specific drawer number where that information belongs. And what's really cool here is how direct this whole process is. See, it's not a search, it's a calculation. You start with any piece of data. We'll call that the key. You run it through the hash function, and bam, it instantly spits out the index, the exact address where that data lives. It's almost like having a calculator that can tell you the exact page number for any word in a book. So if we peek under the hood, this function is actually a two-part machine. The first part, the HashCode map, its whole job is to turn any kind of data, even text, like someone's name, into a gigantic integer. Then, the second part, the compression map, takes that huge number and shrinks it down so it fits perfectly within the size of our table. That gives us our final spot, our index. Of course, not all hash functions are created equal. The really good ones, the ones we want to use, have three key traits. First, they have to be incredibly fast. Second, they have to be deterministic, which is just a fancy way of saying if you put the same key in, you always get the same index out, no exceptions. And finally, and this is crucial, they need to be great at spreading the data out evenly, so we don't get all our files piling up in just a few drawers. But this leads to a really fascinating problem, because no matter how good your hash function is at spreading things out, eventually, it's going to tell two different items to go into the very same drawer. So, what happens then? And you might think this would be rare, but it's way more common than you'd guess. It's all because of a phenomenon called the birthday paradox. It basically says that even with 365 possible birthdays, you only need 35 people in a room to have a really, really high chance of two of them sharing one. The same idea applies here. These overlaps, they happen surprisingly quickly. In the world of hashing, we've got a name for this. It's called a collision. It's what happens when our function maps two different keys to the exact same spot. And this, right here, is the central challenge we have to solve to make our whole digital filing system actually work. So how do we fix this? What do we do about the pileup? Well, luckily, computer scientists have come up with some very clever ways to clean up this inevitable mess. Let's take a look at the strategies they use. It really boils down to two main approaches. The first is called chaining. And this is kind of like saying, okay, this drawer is for all the items that hash to location 5. You just start a little list inside that one drawer. The second approach is open addressing, which has a strict rule. All items have to live in the main table. If a drawer is full, well, you've got to find another empty one nearby. Okay, let's start with the most straightforward method of open addressing. It's called linear probing. And the logic is about as simple as it sounds. If the spot your key hashes to is already taken, you just check the very next spot in line. If that's taken, you check the next one, and so on, until you find an empty spot. So let's just walk through this example. We want to insert the number 18. We run the math, 18 mod 13, and the remainder is 5. So boom, it goes into index 5. Simple enough. But then along comes the number 44. Well, 44 mod 13, the remainder is also 5. It wants to go to the same spot. So since 5 is taken by 18, linear probing just says, okay, try the next one. Slot 6 is empty, so 44 goes there. You can see the same thing happens with 32. It hashes to 6, finds it's taken, checks 7, sees that's taken, and finally lands in the empty slot 8. But you can probably see the problem here, right? This super simple approach creates something called primary clustering. Items just start to clump together, and this creates these long, unbroken blocks of occupied slots, which are basically like traffic jams for our data. Now, if we want to find something, we might have to search through that whole clump one by one, which, well, it slows everything down.
So to fix that problem, we need a smarter approach. Enter double hashing. This is where things get really clever. Instead of just stepping one spot at a time when there's a collision, we use a second, completely different hash function to calculate a unique jump distance for each key. So one key might jump 3 spots at a time, while another one jumps 7.
Now watch this. Just like before, our key 44 hashes to location 5, and it sees 18 is already sitting there. But now, instead of just meekly checking slot 6, we use our second hash function, and it tells us to jump 4 spots. So we check location 9. Whoops, that's taken 2. So what do? We jump another 4 spots, which wraps us right around the table, and we land in the empty slot 0. See? We completely avoided that traffic jam that was forming around slots 6 and 7.
And there you have it. That's why double hashing is so much more effective. By creating these unique, variable jump patterns for each key, it totally breaks up those clusters before they can even get a chance to form. And that leads to a much more even distribution of our data, which just means faster performance all around. And I mean, the numbers really don't lie. Take a look at this chart. This shows what happens when the table is 90% full, a really stressful situation. With linear probing, you're averaging 5.5 checks just to find a spot. That's not great. But with double hashing, you're down to just 2.5. It stays way more efficient, even when space is really tight. So you see, hashing isn't just some abstract concept from a computer science textbook. It's this fundamental hidden engine that's running quietly in the background, making so much of our digital life possible, from databases to keeping passwords secure to making websites load fast. It's this incredible trick of creating order out of what could be chaos. And it really makes you wonder, right? Where else in our world might this elegant idea of a perfect organized filing system be at work?